Welcome to our talk on network infrastructure for generative AI models at Meta. My name is Pavan. I'll be giving this talk together with Gangidi, also at Meta. Generative AI models at Meta are fairly recent. We started 2 or 3 years ago developing generative AI models. We started with the Llama series of models that we released a few years ago, followed by Llama 2 last year. And most recently, this year, we released the Llama 3 series of models. These generative AI models, including Llama, are meant for building new creative applications, building out new creative content, expanding the possibilities of what kind of creative usage our users can come up with. Llama 3, as I mentioned, was recently released. It was released in three forms. There was a small model with 7 billion parameters or 8 billion parameters, followed by a 70 billion parameter medium sized model, and finally a large dense model of 405 billion parameters. This is the largest dense model that we are aware of that is used in production today. And it's quite competitive with very large models available across the industry, as shown on some of the charts over here on this picture. Now, Llama 3 is just a mathematical model in the backend. There needs to be a product that you can use to interact with this model. That's where Meta AI comes in. Meta is a product that is supported across our family of apps, Facebook, Instagram, WhatsApp, and so on, which allows you to enter your queries and interact with the Llama series of models in the backend and get responses for. You can see a picture of Zuck over there in the corner presenting the Meta AI product and how it integrates with our Llama mathematical model. Okay, let's look at the progress we have made on generative AI and Llama in particular over the last few years. The left picture over here, it's the same prompt. All these pictures use the same prompt that is provided at the top over there. The left picture is generated in 2022. This was based on Llama. It generates a picture based on this prompt, but the picture is good, but you can tell that it's cartoonish in some sense. As we move forward in about 6 to 9 months, around mid 2023, we used the same prompt and generated the picture again. We can see that the quality of the image is much better. It's much more realistic. There is a lot more like pictures. It's much better quality, much more realistic picture that got generated. That's with Llama 2 in 2023. Moving forward to this year, we can see that the picture is even better. It maintains the quality and the photorealistic nature of the picture and adds more colors and more vibrance to the picture to overall improve the kind of quality of the output that you are seeing. Now, quality is just one part of the model. Of course, you want a very high quality model, but the second part of the equation is speed. Users want high quality models, high quality responses, but they also want it fast. Now, these two are very strong duals. It can build a very large model that gives you very high accuracy, very good responses. But by doing that, you would make the responses slower. You will make the serving of that model very slow. So the trick is to get both of these together. You want a very high quality model, but you also want to serve it fast. And that's where the infrastructure comes in. That's where your GPUs, your network hardware, and the rest of your hardware and software ecosystem comes in to speed up how fast we can train and we can serve these sort of large models. Okay, let's look at a quick look at the evolution of the training clusters at Meta. Well, we have been doing AI models for a while now, for many years now, but these were originally targeted more towards ranking and recommendation models. So those have their own set of characteristics and uniqueness, and the clusters were built around the uniqueness associated with these models. We use these clusters as generative AI came on. We use these clusters to train generative AI models as well. We continued that in 20 to 23. And this year, when we started launching Llama 3, we decided that these clusters themselves that were built for ranking and recommendation are not quite sufficient for generative AI models like Llama. So we started building a unique set of clusters, a different set of clusters that are more targeted, better suited for generative AI models. So we built large clusters, the scale of 24,000 GPUs per cluster, multiple of these clusters for Llama training and serving. Okay, let's take a step back over here and start looking at the network and communication infrastructure that we built for Llama. So we will cover this in a few different parts. We'll first talk about the Llama 3 training itself. We'll talk about the performance tuning, in particular network performance tuning that was done to improve the network and communication performance for generative AI models, in particular Llama. We'll spend a little bit of time talking about serving together with the training of the model itself, the inference part of the model. And finally, we'll summarize this and talk about what's next for Meta for generative AI model training. So let's take a look at our comparison of where we started and what changes we had to make. So as I mentioned, we started with ranking and recommendation models. They have their own unique characteristics, as I mentioned. For one, they generally scale to only about a few hundred GPUs. They have a different form of communication parallelism. They are typically built on embedding exchanges that are sparse parameter exchanges, and a lot of data parallelism for communication, for splitting up the data across the replicas of the model. And there is a significant communication between these replicas. And this essentially leads us to a model where we have a full mesh connectivity. All processes are talking to each other across this entire job, which makes it hard from a network perspective to scale the model to very large systems. Generative AI, on the other hand, is a little bit different in that for one, it scales to much larger number of GPUs. As I mentioned earlier, for Llama 3, we scaled to multiple clusters, each with 24,000 GPUs for these models. These models are fully sharded, or in some cases are also use classical data parallelism with application. And they use multiple levels of parallelism together. So for example, they use data parallelism, pipeline parallelism, tensor parallelism, and perhaps even more levels of parallelism to be able to scale to very large clusters, in this case, 24,000 GPU systems. This kind of model makes it favorable to build more hierarchical or Cartesian sort of communication patterns, which are a lot more scalable than a full mesh sort of communication patterns that ranking and recommendation models use. With that, I will hand it off to Adi to tell us a little bit more about our network and communication infrastructure.
Thanks, Pavan. I'm Adi Gangidi. I'm a production network engineer at Meta. I lead our GenAI network performance initiatives. So, Pavan just touched upon how ranking models and GenAI models are different. Prior to talking about performance of GenAI models, we'll quickly refresh on how the workload artifacts, specifically relevant to GenAI, shaped our network designs for our 24K Rocky cluster. The building block of our GenAI cluster is an AI zone. AI zones were originally designed to support ranking workloads and can support up to 3K GPUs in this configuration, and they offer full bisection bandwidth. GenAI workloads, however, can scale up to tens of thousands of GPUs. So in order to form a 24K scale cluster to support these large scale, we took 8 such AI zones and connected them using an additional layer of switching called aggregate training switches. At this layer of network switching, however, we have 1:7 oversubscription. This was deemed okay since Llama 3 training specifically produced hierarchical network patterns like rings or trees, and these can tolerate oversubscription just fine. So now coming to performance, in spite of all of this care that went into our network design, our large GenAI clusters still did not perform optimally out of the box, especially compared to our ranking clusters. Performance was variable and poor for our large clusters of the box. We performed a series of investigations to understand the performance bottlenecks. Armed with this understanding, we tuned the communication library and the network, ultimately resulting in us achieving optimal performance. So why was the performance not optimal to begin with? The first reason is because GenAI workloads evolved to be more sensitive to network latency as the scale of the jobs increased with Llama 3. The reason for this is because of hierarchical traffic patterns like rings that accumulated network latency in order to complete a collective operation. And these hierarchical traffic patterns, as we learned before, are very much a commonplace with Llama 3 training. So the second reason for poor performance was non-optimal load balancing. The work we did in the past with traffic engineering did not scale operationally beyond two network hops. Without these specialized load balancing optimizations, ECMP out of the box for the third network hop produced hash collisions. The reason for this, as you recall, hierarchical collectives don't have enough network flow entropy. For this reason, we implemented flow multiplexing to address this problem, meaning posting data that is meant for a single flow or a single queue pair or multiple flows or multiple queue pairs. Along with this, we also started hashing on the queue pair ID field in the Rocky V2 packet. This helped us realize all the unrealized entropy. With all of these changes, ECMP along with flow multiplexing, using all of this over all three network hops, we got great load balancing. So the third reason for poor performance was that we saw far more traffic on the third network hop, especially compared to our expectation when we did simulations or modeling. This is due to the lack of network topology awareness with the job scheduler. This put oversubscribed network bandwidth right in the critical path. To solve this, we specifically invested in distributed ML scheduler modifications to bring the network topology awareness of all three network hops to the scheduler. We described this approach more in detail in another networking at scale talk focused on network artifacts related to ML scheduling. So given limited time, over the next few slides, we talk about how we deal with network latency. So understand that the work we did to decrease the latency sensitive of the collective communication library and the Llama 3 training workloads overall, we need to understand two fundamental architectural artifacts of the collective library. They are two-sided communication and two-stage copy. So first, talking about two-sided communication, this means that in order for a sending GPU to send data to a receiving GPU, it actually needs a signal from the receiver first. And this signal is a small packet with a metadata of expected data size and memory location. And we call this message as clear to send or CTS. So if this small message gets delayed due to very high network latency on the opposite direction due to buffering, for example, the sender will start sending the data late as well. So now, once a sender receives this clear to send message, it can post the corresponding data from the last compute operation. However, as we mentioned, collective communication library also uses another feature called two-stage copy architecture. This means that the interim GPU HBM buffers that are used to buffer these transfers on the sender to receiver, instead of directly writing from the data from the source compute buffer to the destination compute buffer. So let us call these interim buffers as channel buffers. The size of the channel buffer actually determines the amount of RDMA traffic that can be in flight on the network. Such data is posted as work requests by the NIC. We cannot increase the channel buffer too large, as it can result in too much GPU HBM usage, leaving very little for compute operations itself. You can observe now how two-stage architecture is limiting us from sending smaller messages than even the training workload is capable of. This makes us more sensitive to network latency. As the RDMA transfers complete, the receiver sends feedback in the form of ACK packets to the sender. And the sender uses this as a feedback mechanism to register completion signals for all the in-flight operations it's set in motion. So timely completion signals actually help the sender get ready for the next data transfer operation. For this reason, it's also very important for the acknowledgement packets or ACK packets not to get delayed on the network due to buffering in the opposite direction. So here, in this slide, we describe three things we did based on all the learnings that we just talked about the communications library architecture to deal with the network latency sensitivity and to boost performance. So the first thing we did was to put the critical control messages that we just talked about, this is CTS and ACK, in a different queue, in a higher priority queue, by using network switch ACLs as well as the comms library changes. The second thing we did was to focus on decreasing the impact of the spine switch latency on data forwarding. To accomplish this, we perform spine switch VOQ tuning given their multi-chip and virtual output queuing architecture. So the third thing we do is, while we cannot increase the size of the channel buffers by too large a margin due to memory constraints that we just talked about, we can tweak them ever so slightly to send a slightly larger amount of data in flight, decreasing our network latency sensitivity and improving our ability to saturate the network bandwidth. All of these three changes help boost, for example, our all gather collective performance, which is a critical part of Llama 3 training, by more than 10%. And this was across multiple all message sizes, including small messages and large messages. So we discussed a lot about Llama 3 training performance optimizations. Now, let's get back to Pavan to touch upon the Llama 3 inference or model serving artifacts.
Thank you, Adi. We heard about the network infrastructure challenges for training systems. I'm going to switch gears a little bit and focus a little bit on the network infrastructure challenges for our serving or inference systems over the next few slides. First of all, training and inference are both critical from a end user perspective. Training makes sure that our model is high quality and is very accurate. Serving, we need to make sure that these high quality responses are actually given to the user fast and accurately. Now, from a user's perspective, how this works is that you would go to either Meta.ai website or one of our family of apps, Instagram, WhatsApp, or Facebook Messenger, click on the tiny Meta.ai bubble and ask it a question. In this example over here, we have given a question and the answer, the response that Meta AI generates. So from a user's perspective, this is what you're seeing. You typed in a question, you got a response back. But in the backend, the infrastructure has to do more work in order to facilitate this. And broadly speaking, there are two parts associated with giving a response back to the user. The first part is what is called time to first token. This is the time after you have typed in your question, the time it would take for the first word of the response to come back to the user. That's called time to first token. That's typically in the order of a few seconds. Obviously, we want it to be as low as possible for best user experience. The second part of it is what is called time to incremental token. That's after you have received the first word, how much time does it take to get to the second word, third word, and so on. That's a time to incremental token that's typically in the order of hundreds of milliseconds. And again, we want it to be as fast as possible in order to improve user experience. So in the back end, what's happening is there are two parts to the survey. One is called prefill. That's the part that's most associated with the time to first token. And there's decode. That's the part that's most associated with the time to incremental token. The prefill part is very network bandwidth intensive because it communicates a lot of large messages between the different GPUs. And the decode part is typically very network latency sensitive because it is not sending very large messages. It's sending small to medium sized messages, but it's waiting for each response so that you can move forward with the decode part. So how fast your first byte of data can move between GPUs is very important for the decode aspect of it. I'll focus more on the decode part. The prefill part is more similar to how training systems work. The decode part is more unique to serving or inference. So I'll focus a little bit more on the decode. So from the infrastructure perspective, of course, there's prefill and decode. The way we could think about it is to separate out these two into tiers of GPUs. And there need not be a one-to-one mapping between these. You could have X number of GPUs used for prefill, Y number used for decode. And of course, there's communication within each tier, but also there's communication across tiers, both of which are important for us to optimize. And within the prefill, as I said, we are very large message network bandwidth bound, or for the decode part, we are small message network latency bound. Now, bringing the latency down is a very important but very hard problem to solve in general. For example, bandwidth is relatively easier to solve because it's just engineering. You add more network cables, so more network adapters, we can get a higher bandwidth to the first order of approximation. This network latency, however, it's physics. That's much harder to optimize. Having said that, there are some tricks we can play to bring down the network latency. For example, we can improve the network software stack, latency, the overheads associated with the network software stack. We can use new algorithms that are more network latency sensitive. We can have a tighter coupling between our GPUs and our network hardware to have lower latency, and so on and so forth. Here, I'll give an example of one of the algorithm optimizations that we did, what is called as a direct data access algorithms or flat algorithms for all reduced communication. In this, instead of going through a traditional send and receive sort of paradigm, which could generally add higher overhead, each GPU directly accesses the data from other GPUs in a load store sort of fashion and fuses all of the GPU operations, all the CUDA operations into a single kernel to get the lowest latency that we can get away with at sometimes at the cost of transferring additional data than needed so that we can get the lowest latency. This is just one example. There are many such examples of how we can optimize latency, network latency to get the best performance. With that, let me hand it off to Adi to walk us through the takeaways for our network infrastructure challenges for our training and inference systems, as well as to tell us a little bit more about what's next for networks for Meta's generative AI models.
Thanks, Pavan. So, in summary, GenAI workloads are sensitive to how we design networks, as well as the software we use to abstract these networks to the workloads. With Llama trees training specifically, as well as model serving, we ran into multiple performance problems like small message performance, network latency sensitivity, and load balancing issues. We tuned the comms library, implemented flow multiplexing, amongst many other things, in order to solve these problems. So, what's next? We're not done pushing the boundaries of scale. In the near future, we'll be training much larger models. These will require an order of magnitude more GPUs, all connected by the same network fabric. All of these GPUs won't fit in the same building. So we need to decide if we can still operate a lossless network, or we need to consider lossy protocols for the increased network latency the inter-building communication will produce. Beyond this, for such large models, it would be optimal if the scale-up domain size increases from 8 GPUs today to much larger. But if we build shared memory-based scale-up networks in order to increase the domain size, that comes with a much, much higher reliability bar, which we need to really work on in order to how to meet. For serving these giant models to end users, we need to optimize collectives generated by inference workloads over both scale-up and scale-out networks. We need to specially focus on smaller message sizes, which have not been a principal focus of model training network performance optimization till now. So that's a new charter. That's a new area that we need to explore. Both of these are much harder problems, reminding us that we have a lot of work ahead of us. Overall, it's an exciting time to be working on networking and communications, which are a critical part of scaling GenAI workloads like Llama. Many of you listening to this talk may be working on very similar GenAI infrastructure related problems. We'd love to hear more about your own efforts in this direction and compare and contrast ours. Thank you for listening.